Kale Gullett grew up in western South Dakota and attended the University of Wyoming. He received his Bachelor of Science degree in zoology, more specifically fisheries biology, in 1994, and he received a Master of Science in Hydrology in 1996. After a year with the Forest Service and a private consulting firm in Fort Collins, Colorado, Kale headed west and spent 4.5 years working with the Yakima Nation in Washington State and 4.5 years as a senior habitat biologist with the National Oceanic and Atmospheric Administration based in Washington and working on regional issues across Washington, Oregon, and Idaho. Kale's interests and specialties lie in watershed hydrology, fluvial geomorphology, aquatic ecology, fish passage, in-stream flow science, irrigated agriculture, and reservoir operations and management. Kale has been with NRCS at our tech center here for going on 7 years, and he is a very experienced webinar presenter. So with that, Kale, I'm going to turn this presentation over to you.
All right. Well, thank you very much, Holly, for that introduction, and thanks to everybody out there for taking time out of your day to sit and watch the computer screen. I really appreciate it. I'll get right going because I've got quite a bit of slides today, so I got to get into it so we have a chance of getting done. Working in and around rivers is often accomplished by using tools and concepts of hydrology and fluvial geomorphology, which are two related but specialized disciplines. Today I'll cover some of the fundamental aspects of these two sciences and review some of the influence that land use and management has on stream flow and river morphology, trying to use some examples from different parts of the U.S. Further, I'll suggest some resources that might help you with analysis, as well as a few short primers on river science. As I mentioned earlier, today's webinar is loaded to the brim, so I won't have a lot of time for details on some things that really actually have a lot of details. So please get a hold of me anytime to talk about this stuff or to get additional information. All right. If you're new to work in and around rivers, especially on projects with outside partners or TSPs, you might encounter a bunch of buzzwords, models, and jargon that sounds a bit foreign. And truth is, river work is fairly specialized, and not all NRCS folks are trained as hydrologists or geomorphologists. Many of these river science concepts have found their way into the mainstream only the last 20 years or so. I didn't intend to alienate anybody by today's webinar title. In fact, most engineers receive much of what I'll talk about today during completion of a bachelor's degree, and many NRCS engineers use tools and methods of hydrology and fluvial geomorphology in the design and construction of various conservation practices. Today's webinar is aimed at conservation planners who interact with landowners and partners in the field, and it's intended to provide a broad overview of the elements of river science that define rivers and may suggest why they look or act a certain way. So different professions have different views and perspectives about river corridors. Land planners often consider many aspects of land use and may only include river corridors when their activities penetrate corridor boundaries. For example, wastewater treatment activities can take place in confined structures far removed from a river, but the effects of releasing treated water into rivers is a primary consideration of water treatment planning. Engineers are often concerned with developing and implementing safe and practical solutions to human problems. For example, cities and counties often spend hundreds of hours and millions of dollars designing, building, and maintaining civil works projects that protect infrastructure from flood damage. To complete these activities, engineers sometimes partition river corridors into interrelated sets of theoretical and quantitative equations to describe and predict the effects of different amounts of water in a stream channel. Biologists are usually charged with understanding how physical, chemical, and biological processes affect riverine species and habitat. They commonly deal with managing habitats and populations and are sometimes only focused on these aspects of river corridor management. Geomorphologists, on the other hand, view river corridors as a landscape system responsible for moving runoff and watershed materials from headwaters to the ocean. They're interested in how hill slopes, channel networks, and floodplains respond to factors that change runoff and sediment production. Geomorphology is a relatively new science, born of a marriage of physical geography and geology. So, although each of the different professions I just discussed usually brings different views and responsibilities to a river project, I think they all share similar goals. Things like reducing erosion and conserving soil, improving water quality and supply, enhancing habitat, preserving stream bank function, and creating functional river corridors are common goals that all relate to river conservation. Another commonality of these professions is terminology, although sometimes the definitions differ a bit. If you create a tag cloud of abstract keywords from popular published works in hydrology and fluvial geomorphology over the last 20 years in the United States, you get something that looks like this. Now, some of these terms are familiar but have entirely different meaning when used in the context of river science, especially when you combine 2 or 3 of them. Others are specific to hydrology and fluvial geomorphology. So today I'll use many of these words and hope to explain them in a way that clears and doesn't muddy the water. I'll need a few definitions today, and here's a good resource for most of the words in the previous slide. It was developed by a well-respected hydrologist with the U.S. Geological Survey, and it's available online. The references and resources I'll show today will be listed in a hyperlinked file included in the download package for the webinar. If any of the links are broken, just get a hold of me and I'd be happy to send you a digital or printed copy. So let's start with a definition for hydrology. Hydrology is an earth science that deals with the flow of water across and through near-surface environments. Key elements related to today's talk are how we measure and characterize stream flow and how changes or fluxes in stream flow affect river channels and floodplains. So many of you will remember something similar to this graphic from a junior high science class. The water cycle is composed of many elements driven by precipitation and other factors and includes both surface and subsurface pathways. However, for today's purposes, we're going to focus on the part of the hydrologic cycle that concerns surface runoff, stream flow, river channels, and floodplains. Further, we'll focus mainly on drainage basins as a smaller unit of the planet where one or more rivers affects landscape appearance and function. Basically, a drainage basin is a landform where watershed materials, mainly water, sediment, and wood, move downhill under the influence of gravity. Within a drainage basin, rivers and streams act as systems or machines that manage available resources to accomplish a task. In this context, the primary task of a river is landscape change, collecting materials and moving them downstream. Gravity is the basic energy source, water does most of the work, and rocks, soil, and streamside vegetation, both living and dead, provides resistance to that landscape change. So we'll need a basic stream anatomy overview before going much further. The channel is the part of a stream where water appears, and it's usually bracketed by banks. The deepest part of a stream channel is known as the Thalweg, and it's a German word meaning valleyway. The flat surfaces above and along the stream banks are called the floodplain, and that's where water goes when the channel can no longer contain it. Sediment, in the broadest sense, is the sand, gravels, and boulders that appear in the channel and along the river corridor. And streamside vegetation often relies on the water table associated with the river, and once it ends up in the channel, it becomes large woody debris, or LWD. Now, LWD can play a huge role as a structural element of the river channel and floodplain. One of the fundamental pieces of information related to stream hydrology is stream flow, also known as discharge. Measuring the amount of water flowing down a stream channel can be done with different types of equipment, some simple and some relatively spendy, like the velocity meter this gentleman is shown holding. When stream flow is measured in a channel, it gives you a snapshot in time of how much water was there the day you visited a site. Stream flow is determined by measuring the dimensions of the channel, its width and depth, and then by using meters or other means to determine the velocity of the water flowing in the channel. Once these variables are known, the stream flow can be determined by multiplying the area of the channel by the velocity of the water flowing down it. Since velocity isn't equally distributed across the stream channel, accurate measurements of stream flow are derived by subdividing the channel into equal increments, taking measurements within those increments, and then adding up the individual measurements within each of the smaller chunks. Stream flow is a volume rate function. It's a volume of water moving past a point per unit time. The basic units of stream flow used out there are cubic feet or cubic meters per second. To put a CFS into perspective, it's equal to about 450 gallons per minute. And 1 cubic foot per second flowing onto an acre-sized parcel for 24 hours would cover it to a depth of 2 feet. Since the stream flow measurement only gives you a snapshot in time, we set up gauging stations to record flow over time at multiple locations. I'm sure a few of you have seen things like this adjacent to a bridge over a river. Most stream flow gauges don't record the flow velocity. It varies quite a bit across the channel with water depth and other factors. However, the stage or level of the water in a channel can be measured with some accuracy with minimal instrumentation. Stream gauges measure the stage of the water in the channel, and a basic setup is shown here in the upper left. The stage or elevation of the water surface in the channel can be converted to stream flow by using a stage-discharge relationship shown at the lower left. Flow data collected by folks using waders and meters, as shown a couple of slides ago, can be matched with river stage to develop a rating curve. As you can see on the graph, a stage of 3.3 feet equals a discharge of 4 cubic feet per second. Now, this method's been used for over 100 years at many gauge stations across the country. However, gauges have to be visited regularly to maintain the accuracy of the rating curve. Stream gauges can collect data at a number of different time steps. Some record stage data every 15 minutes, for example. And over the long term, these data allow us to describe how much water was in a stream channel every day of the year for many years. When plotted in graphical form, the data are known as a hydrograph, which shows stream flow over time. This hydrograph shows daily average flow in the Alsea River near Tidewater, Oregon from October 1989 through November 1999. Time is shown along the bottom or x-axis, and discharge is shown along the vertical or y-axis. Every dot represents the average flow for one day, and as you can see, flow in this river ranged from very small to almost 30,000 CFS over the 10 years represented. The span of time represented by gauge data is known as the period of record. So here are the same data from the previous hydrograph, although this time presented as a flow duration curve. And graphs like this allow us to estimate the frequency of flows at a station and are often the result of a cumulative frequency analysis of all available gauge data for a site. On this curve, the highest flows are near the upper left and the lowest flows are at the lower right. Where a hydrograph shows the chronology of occurrence, flow duration curves are developed from all data. The day a certain flow occurred is not relevant. Reading a flow duration curve is easy. For example, the flow at this station that was equaled or exceeded 50% of the time was about 650 CFS. You get this by finding 50 on the x-axis, following the grid line up to the blue curve, and then moving left over to the vertical axis to read the discharge amount. The y-axis is logarithmic, so each major grouping represents an order of magnitude increase in flow.
Whether you've heard of a flow duration curve or not, I would bet that you've heard of one of the ways flow frequency analyses are commonly used. Flow frequency analysis is used to determine things we hear about in the news, like a 100-year flood. A new term here is recurrence interval, or the number of years it takes for a flow of some value to return. The recurrence interval of a 100-year flood is 100 years, and it has a 1% chance of occurring in any given year. Recurrence interval is found by dividing 1 by the exceedance probability. Where duration analysis uses average daily flows, flood frequency analyses use annual peak flows from a gauge. So, if you run through the statistics, you can generate a curve that looks like this. You'd read the value of the 100-year flood much the same way as we determined the 50% exceedance flow in the previous slide. So the 100-year flood based on this record is about 60,000 CFS, shown by the blue lines connecting the x and y axis that intersect at the flood curve.
It's important to pay attention to the way data are represented to get a better idea about the accuracy of probability and prediction. The two charts on the left were developed using the exact same 20 years of data. The panel on the upper left uses log axes, which helps the data fit a straight line that appears to shoot straight as an arrow to some high value at the upper right. The panel on the lower left uses linear axes, which makes the data look quite different, curvilinear in fact. As you can see, bending the predictive line to fit the same high value out at the right takes some imagination and could very well end up in a different place in value depending on how you fit the line. So there are errors and inherent ghosts when using data like this, especially when trying to predict a 100-year event based on only 20 years worth of data. Also, bear in mind that this is probability theory and statistics. Recall that a 100-year flood has a 1% chance of occurring in any given year. However, the chance that a homeowner will experience a 100-year flood at least once over the term of a 30-year mortgage is 26%. All right, so if you've ever need to find streamflow data or are interested in diving into some of the stuff I've just been talking about, I'll go over a few internet resources available out there. The first is known as the National Water Information System, or NWIS, and it's maintained by the U.S. Geological Survey. Information from thousands of instruments, including streamflow, groundwater, spring flow, atmospheric data, and glaciers, are all available at this portal. This graphic shows the front end for active surface water sites across the United States. Each gauging station is a gray triangle. Zooming in on a site of interest will show you the gauges in that area. Clicking on the Access Data link will take you to available data for that site. So here's what the site data interface looks like when you click on that Access Data link. A whole bunch of information can be accessed here, including streamflow, weather, water quality, and river stage. Some stations, like this one for the North Platte River near Northgate, Colorado, also include real-time streamflow data. Real-time data are useful for a number of purposes. For example, these data, accessed last week for the same North Platte River gauge, tells me whether or not I could get my boat down the river without dragging, which the answer to that is probably not, since daily flows are way below average based on the 98-year period of record for the gauge. The average daily flows are these reddish triangles, and here the actual flow observed, for example, on July 12th. Also, if I drove into the nearest town, which is Walden, and walked into the Elkhorn Cafe, where I'd be related to many of the patrons, I'd know who had irrigation water and who didn't because of the low water year in the basin. And this is important because it helps you know where to sit down, because some folks are going to be grumpy. So the National Water Information System makes streamflow and other hydrologic data available to anyone with an internet connection. However, it generally doesn't present data analyzed using statistical hydrology methods in the form of flow durations or flood probabilities. Another application is known as StreamStats, and it uses a powerful set of tools to deliver statistical streamflow products. This graphic shows the front end of the tool, as well as the states, which are shown in green, where the tool is fully functional. Most states are functional or undergoing implementation, and the remaining 12, or the states in white, are slated for completion in the next few years, depending on funding. Within the operational states, and I went to Colorado again, the interface works much the same as the previous NWIS tool. You use a map to zoom in on the area of interest until you find a gauge. Clicking on the gauge gives you access to links that take you to data, which are usually shown in blue and underlined. The data, however, look a bit different than the NWIS interface. And as you can see, this screenshot shows, or I hope shows, that statistical predictors like the estimates for the 2, 5, 10, 25, and 50-year peak flows are given for this location. Another cool feature of StreamStats is that it enables the user to select a point in an ungauged stream or on an ungauged stream to generate drainage basin and streamflow information. You zoom in to an area of interest to the layer where blue line coverages of stream networks from the National Hydrography Database kicks in. and select a point anywhere along a stream, and StreamStats will delineate the basin and then use a number of different types of data and tools to generate streamflow estimates. And here's a shot of the type of data generated from the small watershed I delineated in the previous slide. Now, the software produces a lot of information, including drainage basin metrics, peak and low flow estimates, and flow duration data. However, these data, especially the stream flow, are largely estimates derived using equations, and although they can give you an idea of stream flow and other facets of the hydrology of a basin, they can only get you so far. For example, they shouldn't be used for any sort of design work without calibration at a project site. So how does StreamStats generate all that data? Well, a part of the answer is related to the same factors that affect stream flow from a drainage basin. Many things affect the way a basin cycles precipitation, and how that appears is stream flow. In addition to the type and amount of precipitation, basin geology, soils, size, slope, aspect, and shape and land cover affect the timing, duration, magnitude, and intensity of stream flow at the basin outlet. Precipitation type has a strong influence on the shape of a hydrograph from rivers in different areas. For example, snowmelt-dominated rivers, shown by the red line on this graph, usually have their highest flows in the spring when snow melts and runs off, with low flows over the rest of the year when groundwater takes over. Rivers in the Rocky Mountain states have hydrographs like the red line. Basins dominated by rain, shown here as the blue line, exhibit high flows for 3 to 5 months throughout the winter and early spring. The southeastern United States has a lot of rivers with hydrographs that look like the blue line. Basins with both rain and snow precipitation, shown by the black line, usually have a bimodal or two-humped hydrograph which reflects two distinct periods of rainfall and snowmelt runoff. Examples of these types of rivers can be found along the west and Pacific Northwest coast. Basin scale, slope, and shape influence stream flow and hydrograph shape as well. For example, as shown here on the left, smaller basins produce less stream flow with quicker rise and fall than a larger basin. And as shown on the right, basin slope and shape affect discharge as well. Narrow, steep basins tend to produce sharply peaked hydrographs with abrupt floods, while more symmetrical basins have broader peak flows. In addition, land cover influences the shape of hydrograph. Now, this figure shows the effect of the same amount of rain in two similar watersheds, one forested and the other urban. Now, generally, stream flow for a river draining an urban watershed is flashier, meaning it quickly spikes and recedes to very low flows, especially when compared to a forested landscape. The forested setting processes rainfall differently, primarily due to greater vegetative cover, lack of impervious or hard surfaces like roads and parking lots, and intact shallow aquifers that act like hydrologic capacitors, releasing flows slowly back to the channel after a rain event. So here's an example of how land cover change affects stream flow, using the lower Skagit River in Washington State. This area lies along Puget Sound, north of the city of Seattle. The panel on the left shows the pre-development state of this part of the lower Skagit, and although you probably can't read the legend along the bottom, you may notice that the area around the river is composed of mostly blues, greens, yellow, or orange. Now, this means that the river was mostly surrounded by floodplains and wetlands prior to development. The panel on the right shows the present-day land cover in the same area of the basin. You'll notice mostly white and magenta, which means that land cover has shifted to mostly agriculture and urban uses. Only about 10% of the pre-development floodplain and wetland landscapes exist. And here's the effect that change in land cover has had on stream flow in the Skagit River and 3 other Puget Sound systems, 2 affected by urbanization and 1 not so much. The red markers indicate flood probabilities for 1883, while the black markers show flood probabilities for 2002. Now, peak flows in the Skagit and Mercer rivers have increased by more than 100%. By comparison, the Skokomish and Cedar rivers have experienced much smaller changes, owing to less urbanization and greater retention of forest cover in their upper watersheds. So since land cover influences the frequency and magnitude of stream flow, it follows that there must be some corresponding effect on the way a stream channel looks and functions in response to hydrologic alteration. Now this is a decent segue into a discussion of fluvial geomorphology because, over time, river systems tend to reach a balance between water and the materials it carries, mainly sediment and wood. All right, time for another definition. Fluvial geomorphology is the study of landform changes driven by flowing water. Many talks covering fluvial geomorphology include this graphic in some form, so we'll use it right out of the chute and refer back to it from time to time. Known as Lane's balance, this figure suggests that channel response and stability are dependent on a proportionality or balance between the load and size of sediment and the slope and stream flow of a system. Originally used by the Bureau of Reclamation in the design of stable channels, the simple tool illustrates how altering any one of the four components forces channel adjustment. For example, if you move the bucket of water here on the right side of the balance to the right, the left side would rise up and the needle in the middle would move towards degradation. And this response is commonly observed. Increasing slope or adding water to a system usually results in degradation or incision, with the channel eroding downward, becoming narrower and deeper. You could also include a vegetative component into this relationship because streamside vegetation has a strong influence on channel morphology. A few large-scale physical sideboards dictate the way river basins look and function. Climate, geology, and the physical geography of a watershed govern the amount of water and sediment a river will process on any given day of the year. River channel and floodplain geometry adjust themselves to the prevailing streamflow and sediment regime, and vegetation plays a big part in resisting adjustments. Again, this is the general relationship that Lane's balance captures. At the drainage basin scale, we tend to lump river systems into three parts. Gravity powers the work done, and a number of forces resist erosion along the way. Rivers try to get rid of extra energy and find that balance. So moving from left to right, we have Zone 1, or the headwaters or uppermost reaches of a stream, which serve as the supply zone. Steep slopes, bare, sometimes young landforms, and extreme climate and precipitation ranges supply sediment to river channels. Zone 2, also known as the transfer zone, is where rivers begin to respond to the materials delivered from upstream. Floodplains become more extensive, channel morphology can be diverse, and streamside vegetation plays a bigger role in floodplain and channel structure and function. Zone 3, the deposition zone, is where we see the largest rivers in a given landscape, extensive floodplains, and wide, deep channels. So when you assume that river systems are organized from headwaters on down, we can make some generalizations about the basic architecture of any river from headwaters to the ocean. As you move downstream, slope and the average size of bed material decreases. Stream flow, channel width, depth, and average velocities increase. In addition, the average amount of sediment stored in the channel and floodplain increases, as does the relative influence of vegetation. As I mentioned in the previous slide, river channels and floodplains adjust to fluxes in water and sediment over time. And these are known as alluvial systems and are often referred to as self-formed because of their plasticity to changes in stream flow or sediment regimes. Think of Lane's balance. Non-alluvial channels, on the other hand, are those not formed in alluvium and tend to remain functionally stable over long time periods. Any river in a bedrock canyon is a good example. I've talked about floodplains, and you may have heard of river terraces. They're related to one another, but are significantly different. For alluvial rivers, a floodplain is the surface adjacent to the river channel, built and maintained under the present stream flow and sediment transport regime. It's a geomorphic surface, and I'd like to point out that the 100-year floodplain you hear about relative to FEMA and flood insurance may not always be related to the geomorphic floodplain. Sometimes it's an administrative boundary that changes after a flood. Terraces are abandoned floodplains that are usually associated with a different river than you see today. Here's a shot of the Snake River at the foot of the Tetons, showing the floodplain which brackets the channel on either side. And above there, you'll find terraces, which in this setting were formed by successive periods of glacial advance down the valley and retreat back up. Again, these terraces are abandoned floodplains of a much different Snake River. So let's get into some of the specifics of channel form, function, and process. Specifically, we'll cover the following categories of metrics used to describe and analyze stream corridors. Profile describes the form and shape of a river from headwaters down. Pattern or plan form is how a river looks from above. And dimension includes elements of a river's size and shape that vary with stream flow, sediment, and the influence of vegetation. Channel profile describes the overall longitudinal shape from headwaters to mouth of a stream system. It's a fairly intuitive concept. Water flows downhill. Base level is a concept that describes the factor that limits how far in the vertical or elevation direction a channel can erode or aggrade. For all rivers, the ultimate base level is global sea level. However, local controls on base level are afforded by dams, large landslides, and geologic factors such as waterfalls. Now, rivers are generally lumped into one of four channel pattern categories that are commonly recognized according to appearance, as well as physical variables such as slope, number of channels, vegetative characteristics, and the size of material comprising the bed and banks of the river. These four categories are straight, braided, anabranched, and meandering. Now, bear in mind that each of these can exist within the same river along its entire course. Channel pattern can be referenced at a variety of spatial scales. Straight rivers, or even straight reaches of rivers, are relatively uncommon in nature. Straight rivers are relatively unstable, and while they may have a slight bend or two like a meandering river, the location and occurrence of these bends appears to be largely random. Naturally, straight rivers are associated with bedrock, faulting, or other tectonic features. The most common examples of straight river reaches in the present day are commonly associated with human modification. Braided rivers are common at high latitudes and altitudes and likely reflect what all rivers on the planet looked like before the advent of vascular vegetation about 400 million years ago. Today, many braided systems are associated with glaciers or in low gradient streams dominated by sands and small gravels. Braided rivers have many channels separated by high spots or areas of very shallow flow. Braided river systems exhibit complex flow patterns that can change over short periods of time. Consequently, channel migration rates can be extreme, and the amount of material moved can be high but irregularly distributed across the channel. Braided rivers are commonly devoid of vegetation. Braided channels are often seen after debris flow events for some period of time until the river is able to rework itself into the pattern that existed before an event. Another channel pattern I'll discuss today is known as anabranched. At first glance, it resembles a braided river, many channels with islands in between. The main functional difference between braided and anabranched rivers is the presence of vegetated islands. Although some geomorphologists don't recognize this as a major group, I include it here for two reasons. First, there's strong evidence that anabranching is an intermediate step between a braided and meandering pattern, and second, anabranched rivers highlight the important role of vegetation in keeping rivers together. In fact, there's an interesting bit of work out there that details the change in river morphology from meandering to braided after the Permian-Triassic extinction event that killed the dinosaurs. Terrestrial plants died as well, and rivers changed from meandering to braided in a relatively short period of time. The final pattern we'll discuss today is meandering. And meandering rivers wander from side to side along a floodplain in a pattern resembling a sine wave. Meandering doesn't have to be contained within the banks of a river. Here, it's a purely hydrodynamic phenomenon. This slide shows meandering in the Gulf Stream off the east coast of the U.S. in the fall and winter of 1996. Hopefully you can see the meander patterns in the main current, as well as rings that have spun off as the meanders migrated across the ocean. And here's a large meander loop formed by meltwater running off the surface of a glacier. The meander pattern is nature's way of minimum uniformly distributed work. So before talking more about meandering channel types, I need to talk a little bit about the relationship between stream flow and channel form. Major floods have the capacity to do a tremendous amount of work, but they occur infrequently and thus aren't able to totally account for the morphology of rivers and floodplains over time. On the flip side of the coin, low flows are the most frequent, but since they lack the competence to move large amounts of sediment, they don't have much influence on channel and floodplain morphology. So that leaves something in the middle, medium flows that occur on a relatively frequent basis, lasting a few days or weeks every year or two. So the medium flow that's received the most attention and research in years past is known as bankfull flow. Here defined as the discharge where water just begins to leave a stream and spread out onto the floodplain. Commonly, this discharge occurs every 1 to 3 years, on average, in stable alluvial temperate streams. However, bear in mind that there's a good bit of variability within the return interval of bankfull flow, depending on where you're at. Graphically, bankfull stage, or the level of water in the channel that coincides with the bankfull discharge, appears as the dotted line above the light blue band in the graphic shown. There's a bunch of research out there done over the last 50 years that details correlations between drainage basin area and bankfull flow. In addition, there are numerous instances where channel dimensions like width and depth, and thus channel area, are a function of bankfull flow. And these correlations allow folks to develop predictive relationships of channel dimension as a function of drainage area, known as regional curves. So bankfull flow is one important driving factor behind the shape and appearance of a stream channel. Over the long run, bankfull does most of the geomorphic work by transporting bed load, maintaining channel form, and driving channel migration. Bedload transport begins at flows equal to about 60% of bankfull in a gravel channel, and most particles will be in motion at about 90% of bankfull flow. So if you see a channel flowing at bankfull, you can assume that many of the particles inside that channel are moving some way or another. And here's a shot of Young's Branch near Groveton, Virginia, within a few inches of bankfull stage. So identifying bankfull in the field can be difficult, and it's often the source of a fairly significant range of error. Now, some systems lend themselves to easy identification, and others have been modified to the point where finding bankfull can be difficult. These are a few of the more commonly used indicators of bankfull flow. Here's a cross-section from a small stream in Surry County, North Carolina. The red lines indicate the channel cross-section and an estimate of where bankfull stage would be found. It's coincident with the top of the bar surface along the right-hand side of the picture. But again, there are quite a few streams out there where identifying bankfull stage can be difficult or entirely inappropriate given watershed condition and channel type. Okay, so back to meandering. Meandering rivers are the most common pattern in the world, and as I showed a few slides ago, the pattern exists in nature outside of river settings. Now, meander patterns can be predictable. One complete sequence occurs about every 10 to 14 bankfull channel widths. That's kind of why I made that little side trip into a discussion of bankfull. Within a meander sequence, the primary structural channel units are pools and riffles, and they're spaced about every 5 to 7 bankfull channel widths apart. And finally, meanders can persist over long time spans. Well-developed meander patterns carved into bedrock can be found all over the world. And here's an example of a meander pattern that's remained stable over a long span of time. The meanders of the Colorado River have kept pace with the uplift of the Colorado Plateau, which is a process that started millions of years ago. As I mentioned, the length of a full meander sequence, or wavelength, is related to bankfull channel width. Now, this red line shows one meander wavelength, and the distance from end to end is equal to about 12 bankfull channel widths in this river in Wyoming. As you can see, the winding channel is longer than the straight line distance down the valley. And this concept, which can be measured, describes the sinuosity or bendiness of the river. Higher sinuosity means the river is more bendy. Within a meander wavelength, the primary structural elements are pools, which are low spots in the stream, and riffles, which are high spots. As I mentioned earlier, these channel units are often spaced from 5 to 7 bankfull channel widths apart. Some interesting hydraulics operate in meanders that both maintain channel morphology and enable the channel to move across and down the floodplain over time. Flow along the outside margin of a meander bend, which is shown here in red, excavates the outer bank and moves material downstream. When water flows into the bend, it generates a corkscrew-like motion known as helical flow that rotates from the channel bed upward toward the stream bank. This gives the river a lot of scour or erosion ability to move the bank over time. Material eroded from the outside of a meander bend is dumped in a process known as deposition along the inside edge of downstream meanders, and these depositional features are known as point bars. Now, the scour and fill action of meanders creates pools and riffles as bends are scoured and bars are deposited. The migration of meanders by scour and fill drives floodplain evolution, and exposed bars are colonization sites for riparian vegetation. Here's an example of channel migration and floodplain evolution moving from right to left along the Bow River in Alberta, Canada. The tip of the point bar along the left margin of the photo is relatively barren, but as you move up onto the floodplain, you begin to see at least 4 different age classes of cottonwood trees. Aging these trees would enable you to determine the relative age of the point bar as well as channel migration rates. So over time, meanders move across a floodplain, leaving scars where former main channel positions have been closed off. Floodplain features like meander scars and oxbow lakes help you identify the lateral extent of the active floodplain. Okay, now a few slides on the basics of sediment transport, or how sediment moves in river channels. As I mentioned earlier, sediment generally includes a range of materials from very small to very large, like a boulder. Sediment transport mechanisms are commonly broken into 3 categories related to the size of the material in transport: wash, suspended, and bed load. Wash load, which is also known as dissolved load, isn't a big player in the morphology of channels and floodplains. However, suspended load and bed load are basic building blocks in stream channels and floodplains. Suspended load is mostly composed of silts and clays transported aloft in the water column by turbulence, hence the name. It's the largest component of the total material transported by a river or stream, and it's said to be supply limited. The amount transported is limited only by the supply on hand. It plays a big part in channel and floodplain maintenance and can be a significant water quality problem if the stream is out of balance or land use introduces a bunch of fine sediment to a system. Bed load, which encompasses everything from sand up to large boulders, has a strong influence on the morphology of a river. Bed load moves in a layer immediately above the bed of a river by sliding, rolling, or bouncing along. Measuring and predicting bed load is notoriously hard and error-prone, and one of the problems with bed load is that it moves in irregular waves or bursts that don't lend themselves easily to prediction or measurement. Bed load is transport limited, meaning that it can only be moved when flows get high enough. So combining all these concepts allows us to evaluate or describe what happens when changes are made to the water, sediment, and large wood regime of a river. Most rivers across working lands have been modified in one way or another, and responses to these modifications is a whole nother talk. However, in the last bit of our time today, I'd like to cover 2 of these cases: channelization and the effects of dams. Rivers are often realigned and placed into engineered channels in an attempt to protect adjacent land uses from flooding. Here, the Walla Walla River was placed between levees in 1963 to protect orchards and other high-value crops. However, a big flood in 1964 breached the levees, and the river assumed a fairly obvious meander pattern as it migrated beyond its constructed margins. Other changes can be less dramatic but end up looking the same over time. Many stream channels were realigned and straightened in an effort to control drainage and maximize farmable acreage. And here's an example of a reach of stream channelized sometime in the 30s. The red X serves as a registration point to anchor your eye through the next few slides. Some 40 years later, in the absence of continued manipulation, the channel has changed quite a bit. You can see that it's assumed a meandering pattern. The light unvegetated bands adjacent to the meander bends are point bars, and we're starting to see some streamside vegetation. Jumping ahead another 20 years, the channel has expanded its meander pattern, point bars are more extensive, and streamside vegetation continues to increase. And by 2002, we see what appears to be a vegetated buffer. The meanders are more strongly pronounced, and streamside trees are more prevalent. There even appears to be a channel shift near the bottom of the photo on the opposite side of the floodplain from our red X. And here's a shot from 2007, this time in color. Not a lot of difference between this and the 2002 picture, except that the meander loops have extended and moved down valley, and the riparian corridor appears a bit more continuous. So over the last 80 years, or almost 80 years, represented by this sequence of aerial photos, the stream has changed quite a bit from its channelized condition in the 30s to the meandering system bracketed by a decent riparian corridor in 2007. Now, this same sequence of events can be found in hundreds, maybe thousands of stream miles across the eastern and midwestern United States. I like to use the preceding slides because they illustrate an important tool in fluvial geomorphology. The channel evolution model, originally developed by Shum, Harvey, and Watson, first published in 1984. In short, the model describes a sequence of 5 relatively predictable stages in the recovery of a channel from major disturbances like forest clearing, urbanization, dam construction, or channelization. The end stage, or point where the channel reaches equilibrium, results in a mini-me, or small version of the original channel, inside of a smaller floodplain that's inset into terraces composed of the pre-disturbance floodplain. The model accounts for many of the processes in fluvial geomorphology that I covered today, channel pattern and slope changes, the development of bars and structural units like pools and riffles, revegetation, and changes in sediment size and composition along the channel as it attempts to balance itself are all accounted for by the model. Further, when applied to a channel that hasn't reached equilibrium, the channel evolution model provides a sort of roadmap for future changes that will likely occur over time once you've figured out what stage of recovery or evolution the channel you're looking at is in. So as you might imagine, dams have a strong effect on rivers, both upstream and downstream of the dam itself, and here's a well-studied example from the West Coast. Trinity and Lewiston dams were built on the Trinity River in California and were finished between 1962 and 1963. Each of these 2 facilities provides storage for irrigated agriculture and produces hydropower. Now, downstream of the 2 dams, the Trinity River, at a place known as Gold Bar, looked like this in 1961, prior to the closure of the dams. Notice the relative width of the channel and the presence of an island in the middle of the river. Here's the same location seen in 1970, about 7 years after the dams were closed. Now, since the dams both decreased stream flow to this reach and captured all the sediment that once supplied this part of the river, you can see that the channel width is decreased and vegetation has started to encroach and narrow the channel. The margins of the island are covered by vegetation, and the channel of the river along the left side of the island, which is towards the lower right of the photo, is barely visible. Here's the same location shown in 1997. Streamside vegetation has increased in age and structure, and the channel flowing along the left side of the island has been closed off. The remaining main channel has become narrower and deeper than the pre-dam condition. Now, the river's response to damming shown at this specific location can also be seen for many miles downstream. So Trinity and Lewiston dams trap most of the sediment that once supplied the channel, and their operations and resulting outflows generally scour smaller material from the downstream channel reaches. The main channel became simplified and floored with larger sediments that no longer move frequently under the new flow regime of the river. Although operational changes to the dams in the late 90s helped restore some of the geomorphic forces that maintain the channel, there's still a profound lack of diversity and habitat. So a combined effort of state, federal, and tribal entities is working to inject gravel back into the channel in an effort to replenish channel structure and provide better spawning habitat for native fish. Ongoing studies are attempting to quantify the effects of gravel injection on the morphology and function of the Trinity River. All right, my final example for the day looks at what can happen upstream of a dam and incorporates the concepts of base level change, urbanization, increased sediment production, and the role of riparian vegetation in channel stabilization. Conisty Dam on the Reedy River near Greenville, South Carolina, was finished to its present-day form in 1892. It was built atop bedrock control in the river, but increased the height or base level of that geological control by about 28 feet. The dam formed Lake Conisty about 6 miles south of downtown Greenville. So here's what Lake Conisty looked like in 1943. The dam is shown by the red arrow near the lower right of the photograph, and a red star indicates the location of a feature known as Taylor's Island. The red and black dashed line indicates the perimeter of the lake at the time the dam was built. Now, as you can see, the channel of the Reedy River, indicated by the blue lines, has already started to reclaim the former lake. And here's an aerial of the lake from 2009. The location of Taylor's Island, perimeter of the lake, and location of the dam are noted using the red star, dashed line, and arrow, respectively. So Lake Conisty is almost completely filled with sediment, and areas of formerly open water, more than 20 feet deep, are occupied by a river channel and a vegetated floodplain. And finally, a shot from 2011. The dam imparted an increase in the base level of the Reedy River in this reach of about 28 feet. As the Greenville area developed, changes in land cover contributed sediment to the river that couldn't be passed by the dam because of base level rise. The dam created a big flat spot in the river that extended for quite a way upstream, and this slow reduction equated to a reduction in sediment transport capacity that resulted in deposition. If you look at a time series of aerial photos of the area, the site looks much like the delta of a large river emptying into the ocean. As this delta created new geomorphic surfaces, vegetation became established, defended the floodplain from erosion, and a meandering channel developed. As you can see at the lower right of the photo, the new channel now ends only a few feet from the crest of the dam. This is a really interesting site, the destruction of a lake and creation of a river channel in less than 100 years. Sometimes things happen fast along rivers. So much of this information can be found all over the internet in numerous textbooks and thousands of journal articles. But I think there's a few out there, a few short primers, that are pretty good reads because they're short and written without too much technical gobbledygook. The first is called Stream Dynamics, an overview for land managers, and was written by a distinguished Forest Service hydrologist named Burchard Heed. Next, I'd recommend Chapter 7 in the Big Blue Book, NEH 653. I'd also recommend Appendix A of the Stream Simulation Culvert Guide I've spoken of in other webinars. Although the guide is focused on culverts, Appendix A is a great overview of stream geomorphology. And finally, I'd recommend Going with the Flow, Understanding Effects of Land Management on Rivers, Floods, and Floodplains. This was a cooperative effort between Oregon State University and Oregon Sea Grant written for land managers. All right, that's it for today. You've sat through a relatively epic amount of material, and I really appreciate your time and attention. Before I turn this over to Holly, I'd like to mention another webinar slated for the end of January 2013. The working title is Urban and Channelized Streams, Working in Highly Modified Environments to Enhance Stream Function and Habitat Quality. So with that, we'll turn this back over to Emily or Holly and maybe have a few questions. Be pleased to hear comments or questions, and again, thanks for your time.
If you'd like to ask a question, you can dial *1 on your phone to put yourself into the queue. You can also use the Notes tab on the top right of your screen.
Thanks, Emily, and thanks, Kale, for a very informative presentation. Your slides are always just really interesting to see and to watch the sequence of events that takes place over time. We've got a series of questions that are kind of true and false type things. Let me start out, though. One person is asking about the hold on a second. Scroll past the one I need here. Yep. Okay, the USGS Stream Stats site looks to be a powerful tool. The person is asking for the website, or is there another way that you plan to provide that information?
Well, yeah, as I said, what I've got is a single Word document that is going to be part of the download materials for the presentation. But the actual web address is streamstats.usgs.gov.
Okay, that's a simple one. All right, let me move to the next question. The question is, the NRCS Hydro, is that a tool that can be used by non-engineers for watershed analyses? Is that something that you have familiarity with?
Well, I think I do, but you know, I'm not to the point, at least presently, where I feel comfortable enough to answer the question. I guess that's one of those where you'll have to say, would it be okay if I got back with you to answer that question before I shoot my mouth off and say something wrong?
Okay, well, we'll make sure. I'm sorry.
I'm sorry. Yeah, as long as we can get the question asker's name, I'll be more than happy to try to collect my thoughts based on where NRCS Hydro is at this time. I haven't been involved with that for a couple of years, I suppose.
Okay. All right, here's a true and false question, and you can comment as needed. Meandering appears to be a way for a stream to manage its energy. Is this a true statement?
Yes, I think that, you know, if you think about any of the pictures that you've seen of, maybe if you're familiar with a lot of the works of Luna Leopold, train wreck in South Carolina that had a bunch of really long rails on it. When it wrecked, all those things were compressed into these really, I guess I probably should say it about a train wreck, but beautiful sine wave looking forms. And I think, again, the most sort of common way of minimum variance in the context of some famous hydrologists is that, you know, meandering is nature's way of minimum uniformly distributed work.
Okay, next question. 2-year storms are the channel forming flows. Is this true?
Well, again, you'll hear all over the place that the return interval or the recurrence interval for bankfull is roughly about 2 years. And I think that there's a pile of data out there that would support that, especially in stable alluvial temperate streams. But as you move into systems that have been modified, again, where sediment and stream flow have been affected, or if you move into settings where, for example, the American Southwest, a channel-forming flow may take 90 or 100 years to happen. And that's, again, based on precipitation and climate. So, you know, I think sometimes we're saddled with a lot of these rules of thumb. By and large, I think, you know, for a lot of the places NRCS works in the lower 48, especially in the Midwest, a 2-year storm could be considered the channel-forming flow. But again, we're kind of getting into some details there, especially where bankfull flow and effective flow have been confused a little bit. So, but as a rule of thumb, I think it's a good place to start. And then you can either change, you know, you can either increase or decrease that return interval flow depending on where you're at based on some field data.
Okay. Emily, are there any questions that have come in on the audio?
No questions on the line.
I think we are becoming a notes webinar question and answer period. We've got a couple of people, Kale, that have passed along their compliments on your presentation. Thank you, Carl and Todd. And also, Carl indicates that please do, and it's okay to get back to him on the NRCS Hydro.
Great.
Karen is asking the question, will the PowerPoint presentation be available for future reference? And I would say that yes, we always make the webinar replay and a version of the presentation file available for you after the fact. Those are available at our Tech Center website and the Science and Technology Training Library for NRCS employees. Let's see, Dan is asking a question. Does SVAP2 reflect what we have discussed today?
Yeah, you know, actually, quite a few of the slides and the probably too many that I presented are drawn directly from the set that I use for a one-day SVAP workshop that that I've taught in a few places, and it's a great question, and thanks, by the way. It does do everything it can, SBAP does, to try to capture the various types of forces that affect, stream condition, both visually and functionally. So, for example, in 2007, I guess, when we rewrote SBAP into its current version, SBAP 2, the channel condition element is largely composed or comprised of the channel evolution model, in an attempt, really to capture the fact that an awful lot of the streams we work on, are meandering systems in working lands that have been modified to some extent or another.
Okay, we've got one more question from Brett. Brett asks, could you please offer your professional view of the difference between form and function-driven fluvial geomorphology theories? That's a big one.
Well, there's a big one, and that might be Brett Fessel from Michigan. I'm not sure if it's the same person, but at any rate, there's, I guess, if I understand the question correctly, I think that there's getting to be a couple of big camps or schools of thought out there in the term, or I guess in the world of geo-fluvial whiz-bang stuff, form versus function. And I think that when you talk about estimates or classifications according to form, or how a river looks, obviously they're based on data, and I think a good example of this would be Dave Rosgen's stream classification system. Based his development on that, on data that were collected, starting in the early 80s. The first paper was published in 1994, and it's been going strong here. I think that the danger here is where you start to extend form-based theories in fluvial geomorphology into places that don't capture the same types of settings where the original data were collected, for example. If you look at streams in Maine, a lot of the things that you'll see in Maine, although recently glaciated, you'll see an awful lot of channels that look like they fit Rosgen's classification system or form-based approach. They don't really, once you start getting into some of the pieces and parts, there's places where it just doesn't make any sense. And so then I believe it's better to reach back into your toolbox and go with something that is more focused in function, focused on the processes in play that might be responsible, at least over the last bit of time that we've, that we're able to sort of evaluate the functions that occurred out there that make a channel look the way that it does. So I guess my real professional view is that they are, first and foremost, form-based is excellent for helping people immediately get an idea in their head of a stream when you want to talk to somebody on the phone. But sometimes in terms of trying to figure out design or what factors might be leading to bank stability problems, then you have to be able to shift gears and go into function or process-driven stuff.
Okay, well, you must have hit the nail on the head because you've gotten applause on that answer, Kale.
Right, that's all.
Okay, we got one more in the queue. The question is, the use of woody debris in a stream can be good for stream habitat. Do you agree?
I do agree. I think one of the problems we've run into in the past, especially when it comes to things like stream restoration, is the idea that, well, wood is good, so let's throw it out there. And then, of course, what will happen is, since maybe the wood is too small for the stream, people will want to pile a bunch of rocks on top of it to hold it in place, or go to great lengths to cable it down. And so, along the lines of this, the previous question, it's one of those times when I think a function-driven or a process-based approach to geomorphology is good, and it's good because you need to be able to place how wood reacts in a system, especially in the context of where you're at. Obviously, woody debris in the eastern United States is nowhere near what it used to be. That's an incredibly interesting topic if you start to kind of dive into historical literature as far as what the Mississippi looked like, or in the New England states, what the size of an old-growth tree was up there. It just blew away. And when you take that information, like just the size of wood and what effect it likely had on streams, the watersheds we're working in today are nowhere near what they used to be like. So, but as a general question and answer, yeah, habitat-wise, wood is good.
All right. Well, I'm not seeing any more questions coming in, and you've been on the hot seat for about an hour and 10 minutes now, so I think we'll just conclude the webinar at this point. And again, thank you, Kale, for the excellent presentation.
Thank you, Holly. And thanks to everybody else.